Homework 14, Logarithmic Functions, Video 3, Evaluating Logarithms and Exponent Rules, Part 2. Before we get to these two examples, I need to finish something that I didn't finish over here. I wrote an exponent rule, but I didn't write its corresponding logarithm rule. And they're starting to run into each other, so we'll partition them. The exponent rule that was introduced in the previous video is that when you raise a number to a fraction power, the numerator actually is a power, but the denominator is the index on a radical. So how can we use this to write a logarithm rule? We can say that log base b of the nth root of b to the m is equal to m over n. Because this is the power you would put on this base to get that argument. It's one of the more obscure rules, but I know it shows up 2 or 3 times in this and future homeworks, so it's a nice one to have at your disposal. All right, so we're going to invoke a couple more rules, but these will actually be logarithm rules and not exponent rules. So I'm going to erase this, and as necessary, I'll write those again individually. And while I'm at it, let's go ahead and number these. 1, 2, 3. And any other time we run across a property that we can, a problem that we can extract into a specific property, we'll add it to our list of rules over there. So let's take a look at this one. Log base 5 of 5 to the 11th power equals. Now, before you start figuring out 5 to the 11th power, make sure you know the question that you're being asked. Remember, every logarithm is asking a question. The question is, what power turns the base, which in this case is 5, into the argument, which is 5 to the 11th. So, what power would you put on this to make it look like this? How about that power? Isn't 11 the power I would put on 5 to turn it into 5 to the 11th power? As crazy as this problem may look, it actually gives you its answer. The power you would put on 5 to make it look like this is 11. And I didn't even need to know what 5 to the 11th power was. Because the question wasn't, what is this equal? The question is, what is the power? There it is. So we can turn this into a log rule pretty easily. It goes something like this. If you have a log, any base, we'll call it b, and your argument is that same base raised to a power, we'll say b to the n power. Then the power that turns this into that is just n. No work involved if you know the question, what power turns the base into the argument. This last one on this video is not as intuitive as the previous one. This one was easy if you asked the question correctly. What power turns this into that? The 11th power does. But here we're not asked what the answer to a logarithm is. We see a logarithm living where an exponent is. So this is 3 to the log base 3 of 7 power. But with the correct perspective, this is actually pretty easy to answer. Maybe you know what it is and I don't have to show you, but I'm going to anyway. If you were to ask me what's log base 3 of 7, I couldn't tell you off the top of my head. There is a way to get an answer out of a calculator, but I don't know off the top of my head what power turns 3 into 7. 1 is too small, 3 to the first power is 7. 2 is too large, 3 to the second power is 9. So all I know is that the missing power is between 1 and 2. But I'm not being asked what does this log equal, I'm being asked what does 3 to that power equal. The trick to getting this is to remember what the answer to this does. I don't know the answer to this log, but I know what it does. It's the power that turns 3 into 7. So its answer is the power that turns 3 into 7. So I don't know what the answer is, but I know what the answer does. As a power, it turns 3 into 7. Wait a second. Where is that logarithm living? In a power on a 3. So whatever this answer does, as a power, it turns 3 into 7. It's a power on the 3, so by its own definition, it turns the 3 into a 7. Never had to know what the log equaled, but because of the way it was structured and where it was located, I know what it does. Let me say it one more time. Don't know the answer to this log, but I know what the answer does. As a power, it turns 3 into 7. It is a power on a 3, so by its own definition, it turns into a 7. How could you capture that as a logarithm rule? Well, you start with any base, we'll call it b, and in the exponent, you put a log on it. But that log must have the same base. But the argument can be anything, we'll call it n. Whatever the answer to this is, as a power, it turns b into n. It's on the b, so it turns it to an n. It's almost a canceling process. In fact, these two together illustrate that exponents and logs are inverse functions, because the log of an exponential gives you the power back, and the exponential of a logarithm gives you the argument back. So if you really understood the section on inverse functions way back on test 2, I invite you to go back and revisit it, because these two properties help prove that logs and exponents are inverse functions. You still have to check domain range issues, but let's not worry about that. All right, these are not the end of the logarithm rules. As we run across more, we'll list them. In fact, there's one really simple one that I should have picked up earlier, so we're going to pick it up real quick. It should have preceded number 1, so it'll probably be rule number 1.5. These rules aren't in any particular order. They're just in the order that we stumble across them. This one's actually really easy. Don't let the numbers intimidate you. Log base 572 of 572. Think about the question. The question is, what power turns this into that? Well, what power would you put on a 572 so that the answer is 572? In other words, what exponent goes here? And I think it's fairly transparent that it's 1. So a log property that we didn't pick up earlier, we'll call it 1.5 just to put it up here, is if you take a logarithm of any valid base, remember, positive but not 1, and your argument matches the base, then the answer is 1. 1 is the power that turns a base into itself. Real quick, the reason the base can't be 1 is pretty simple. If the base were 1, one of two things would happen. What power turns 1 into 5? No power does, because 1 to any power is 1. So this is undefined. However, if it was log base 1 of 1, we run into the opposite problem. What power turns 1 into 1? All of them. So this can be any value. So having a base of 1 runs into problems because either A, you can't get an answer because you can't get this by sticking a power on a 1, or any number would work because any power would turn 1 into 1. The reason the base can't be negative has to do with the fact that if you put a fraction power on a negative number, you might accidentally take the square root of a negative number and create imaginary numbers, which actually is allowed with logarithms. You can actually put imaginary numbers in them and get them out, but that's way beyond the scope of this course. So a lot of the restrictions are imposed on keeping things defined and real. That sounds a lot like domain. I wonder what the next video is about.